Today we will talk about electromagnetic waves in matter. So before coming on the propagation of electromagnetic waves in matter, we will have a brief revision of what we have studied in our previous lectures as well as in previous classes. So, as I have already told you about these mathematical operators, this is del F. This is gradient of a scalar. F is a scalar quantity, and we are taking the gradient of the scalar quantity. This is the gradient, and the resultant quantity will be a vector quantity. There is another operation that is called divergence. It is taken of a vector quantity, and the result is a scalar quantity. The third operator is the curl operator. It is operator on a vector quantity, and the result is also a vector quantity. Now there are two more operators. That one is the Laplacian operator on a scalar quantity, and the result is a scalar quantity. It's a second order derivative with respect to the directions. And the last operator is a Laplacian operator on a vector quantity, and the result is also a vector quantity with 2 times gradient operator operating on the x, y, and z components. The mathematical identities. The slide is changing or not? I think it is going fine. The mathematical identities that will be useful are double curl of a curl. This is one curl operator. This is another curl operator. These are operating on a vector quantity f. So the standard identity is that this is equal to the divergence and the gradient of the divergence minus the Laplacian operator, the Laplacian vector operator. This is a standard identity that you can use. And the second one is that the divergence of a curl is always 0. Similarly, we do have identities with the sine and cosine functions, but they will not be used in this chapter, so I am skipping them. Next is the Gauss theorem. This is a relation between a volume integral and a surface integral. If we take del of a vector, then the volume integral reduces to the surface integral. That means if we have differentiated this in broader term, we have differentiated this vector A with respect to the axis, we get a surface integral. Similarly, a surface integral can be reduced to a line integral by having a curl operator. We take the curl of a vector, then the surface integral can be reduced to the line integral. So in general, we have already studied the Coulomb's law. So a field theory describes the interaction between two different objects. And according to the Coulomb's law, these two charged objects exert a force on each other. F1 is the force on the first charge due to the second charge. Just notice the subscript 2, 1. And F2 is the force on the second charge due to the first charge. You know the values of these constants? 1 by 4 pi epsilon 0. And this interaction can be expressed in terms of an electric field that is created by the charged object. And we can define that electric field with this expression. And the relation between the field and the force is given by equation 11. The force is a Lorentz force, the electric field multiplied by the charge. You see in this equation, if we multiply this equation by Q2, it will be the same force that we have written on the previous page. This will come. So this is how force and electric fields are related. We have already studied this. This is called Lorentz force. And the equation is called Lorentz force equation. So the another field is the magnetic field. So we have two relations like we have studied in the Maxwell's relation, Maxwell's equation. These are the 4 Maxwell's equations. We have already studied about these equations and the proof. The total force due to the electric and the magnetic field is given by this equation called the Lorentz force equation. This is first term is the force due to the electric field, by the second term is the force due to the magnetic field. And since for the stationary charge there is no magnetic field, so it will be moving with the velocity v. Now, these equations can be expressed in a simplified manner if we express these fields in terms of potentials. So we defined 2 potentials corresponding to the magnetic and the electric fields. The potential corresponding to the magnetic field is called the vector potential. It is denoted by capital A. This is a standard definition, a standard notation. This is the vector potential, and the magnetic field can be expressed in terms of this vector potential. Similarly, we have a scalar potential that is phi, and the electric field can be expressed in terms of these vector and the scalar potentials through this equation. So the two fields are now expressible in terms of the vector and the scalar potentials. And we have seen the relation through expression between the fields and the force. So basically what we conclude that the field is the force per unit charge. Because when we multiplied the field with the second charge, we got the force. So we can define that the field is the force per unit charge, and the potential is the potential energy per unit charge, and the field is the gradient of the potential. Field is the gradient of the potential means is equal to minus del phi. This. So in terms of potential, the Maxwell's third and the fourth, the curl equations, can be reduced to give us two coupled equations. These equations are obtained by taking the curl of these equations once again, applying the first vector identity, this one. So this term will become 0 in our case, and only the second term will remain. This is that second term, and this is term from the right hand side. So we get these two coupled equations. One is in terms of the vector potential and other is in terms of the scalar potential. These are the coupled equations which govern the propagation of electromagnetic waves. These are also called equations of telegraphy. All the propagation of electromagnetic waves in any kind of matter, whatever matter it may be, the propagation will be governed by these two equations. And these two equations can again be coupled to form a single equation that we called wave equation. These are also telegraphy equations, are also wave equations. We have two equations. We can couple them to a single equation to form a wave equation. Now we believe that there are only four fundamental types of fields in nature. The most promising are the fields of the gravity and the electromagnetic fields. The other forces are weak nuclear and strong forces, and they differ both qualitatively and quantitatively from the gravity and the electromagnetic fields due to their length of interaction. Like I talked just now about the equations of telegraphy or the second or wave equation in terms of the scalar potential phi, we can reduce that equation to this. And for a point like source, this equation can be further reduced to this. This equation is a solution of this. This is the value of the scalar potential for a point like source, and moreover the source is static. It is not moving. This is a comparison of the electromagnetic force and the gravity force. The gravity force is less and the electromagnetic force is quite large. All the equations that we have talked about are the classical equations. They don't consider any quantum effects into account. And as you know, the best way to identify an equation, whether it is classical or quantum, is the presence of the Planck's constant h. So up till now, we have not taken this h into account. We have not seen h present in any of the equations. So all the equations we have considered are the classical equations. But we believe that when the particles interact, they do so by changing a discrete amount of energy, and that is defined as quanta. So when we try to develop this classical field theory that we have studied right now, by including the quantum effects, so the new theory that will be constructed by modifying the classical field theory and introducing the quantum concepts will be named as quantum field theory. So in quantum field theory, the force or the interaction between the two particles is understood in terms of the exchange of a third part. Like there is interaction between the two particles. So they will interact through a third particle. Either a particle will be created or it will be annihilated. So there are different models for that. But quantum theory of gravity, or quantum theory of radiation is not in the scope of our syllabus, so we will not go into it. We are limiting ourselves to the classical concepts. I just gave an idea of how the quantum field theory is developed, but we will not go into it. Our goal is limited to the classical concepts. And in our next lectures, we will be studying the electromagnetic waves in different kinds of media. we will be considering only the medias. The propagation in waveguides and the sources of electromagnetic radiation are not in your codes. They are in the syllabi of the higher classes. We'll be limiting ourselves only to this concept of electromagnetic waves in various media. The propagation at the boundaries in waveguides and sources are in higher classes. When you will come to, I think it is semester 4 or 5. So up till now, what we like I have previously expressed that the electric field is the force per unit charge. So in free space, it seems a much simple thing. Now, if we take a dielectric that is non-conducting and we apply a electric field to the dielectric, a dipole moment is created. A dipole is created whose dipole moment is given by this expression, equation 23. And this is the dipole moment of the two charges who have been displaced due to electric field inside the molecule only. This is a molecule, and the positive and the negative charges have been displaced under the influence of this electric field. The negative charges has gone to this end, and the positive charges is on this end. So they have been displaced. So this is a single molecule. But in practice, there are numerous molecules. And the charges, negative charges of all the molecules will come to one side depending on the polarity of the electric field. All the positive will come on one side, all the negative will go on the other side. So this results in a polarization. And this polarization is equal to the dipole moment multiplied by the number of the molecules. Just because dipole moment give us the polarization of a single molecule, and the total polarization is the multiplication of the dipole moment and the number of the molecules, which is given by equation 20. But in practice, this can be taken to be as a proportionality only. The exact value depends on the property of the medium also. So that property is the propagation constant and is called the susceptibility. Because by this expression, you can say that it is a general concept, it is valid for every medium. We have not considered the characteristic property of for a particular medium. So now we are considering if there is a constant for a particular medium. This is called susceptibility, and it is different for every medium. The electric displacement, we have talked about the electric displacement, which constitutes the displacement current. That was a concept given by Maxwell. So the displacement vector can be defined by this equation, where this is the polarization term, and this is an additional term that is contributing to the electric displacement. And remember, this will again contribute to the displacement current in the Maxwell's equation through del D by del T. This polarization we already have seen on the last page. When we substitute the value of this polarization in equation 26, we get this. We combine the terms. And this electric displacement is a measure of the electric field in a material, taking into account the response of the material to the field, which is denoted by the susceptibility. And there is another quantity called the relative permittivity, which is defined in this way. And these two are related by this expression. The susceptibility and the relative permittivity are related by this expression. These are only mathematical concepts. This is the equation. We define this quantity as the relative permittivity. And this is a dimensionless quantity. If the material does not respond to an electric field, we apply the electric field, there is no change, we say that the susceptibility is 0 and the relative permittivity is 1. The susceptibility is 0, but this is the one term. So the relative permittivity will be 1 when the susceptibility is 0. And the material that has a strong response to an electric field will have susceptibility much larger than 0. And the permittivity is defined as the relative product of the relative permittivity and the product permittivity of free space. This you must have already studied in your previous classes. This magnetic field is related to the magnetic intensity through this expression, where the constant mu is the permeability, and permeability of free space is, it has value of 4 pi into 10 to the power minus 7. These are the expressions for the electric and magnetic fields in terms of the electric displacement and the magnetic intensity. These you have already studied this expression. This is in terms of the displacement. The velocity of light in terms of mu 0 and epsilon 0 are expressed by this expression. You already know it. The current density is given as a product of sigma into E. And these are the basic concepts that we talked of today. And in our next class, we will be taking these concepts, we will be applying these concepts for particular kinds of matter.